All right, cool. So, first of all, let's just do a brief introduction to organic chemistry. All right, as you know, this is a separate class from the other sort of branches of chemistry. Organic chemistry very much so kind of stands on its own. Organic chemists tend to be specialized in organic chemistry and only organic chemistry. It's kind of a branch of chemistry, so why? Why is it its own thing? Okay, so first of all, it has kind of some interesting historical roots. There was a time not too long ago where chemistry wasn't even a thing, right? Chemists came along in the scientific revolution and they had one huge win under their belt, which was they predicted that the world was made up of all of these teeny tiny little building blocks we call atoms. That was not a theory that was sort of well understood or even accepted for a very long time. For a very long time, the prevailing theory of how the world worked was a very religious-based reasoning, right? Because God said so, basically. Okay? You had people in very high powers that were sort of explaining the way the world worked, and they were kind of just pulling crap out of their butt, right? It just sounded good. Then all of a sudden we had this scientific revolution that said, well, maybe we should test some of this stuff out before we start believing it. This very evidence-based way of looking at things. And again, chemistry had one big win that we have yet to be able to disprove because it seems to be true, which is the world around us is made up of atoms. Okay? So that's kind of how chemistry got started. So then what about the branch of organic chemistry? Well, still for a very long time, there was this kind of religious influence on science. And there was especially this belief that, okay, fine, the world out there is made of atoms, but we're something special. Life is something divine, and we're not made of that same sort of thing, right? Well, then it turned out that somebody, actually it's kind of an interesting story, they synthesized a compound called urea in the lab, very elementary chemistry techniques, sort of melting point sort of stuff that you would do in an organic chemistry lab. And then somebody isolated that exact same compound from human urine. And all of a sudden it was like, wait a minute, full stop. You mean that what that's made of is the same thing as what we're made of? And that kind of led into this branch of organic chemistry here. Okay? So strictly speaking, nowadays organic chemistry, an organic compound importantly contains two elements. Does anybody know what those are?
Carbon.
Carbon's one of them. So must contain carbon, and the other one is hydrogen. So you will often sort of hear on a more informal basis that organic chemistry is the study of carbon, and that's because, again, carbon is going to be the central atom that we see in our organic molecules. Okay? We don't have a periodic table in here. I'll print some out for you so we have some periodic tables. All right, but just importantly, if we take a look at a periodic table, of course, always important in chemistry. It's marked up from another class. Our periodic table, it has this little staircase in here separating the metals from the non-metals on our periodic table. Carbon lives over here on the non-metal side, and actually hydrogen's in the wrong place. It's also a non-metal. And so what you would have learned in general chemistry is these non-metals form a special type of compound, form a special type of bond with one another called a covalent bond. And so organic chemistry is exclusively the study of covalent compounds, right? Compounds that contain only non-metals. We're not worried about the metals, we're not worried about the salts, that's a completely different branch of chemistry. We're very focused on covalent compounds that contain carbons and hydrogens. Okay? So organic compounds must contain carbons and hydrogens, and again, they are covalent compounds. And this is sort of the basis for why organic chemistry is so distinct, is covalent compounds are quite a bit more complicated than ionic compounds, right? The ionic compounds, a good example of where you see ionic compounds out in nature are in rocks and soil and that sort of static kind of compound here. life is all made of covalent compounds. And covalent compounds, again, the chemistry of those covalent compounds is just a little bit more complicated. So that's why we have this segmented branch of organic chemistry. All right, and so because of that, one very key thing that we're going to see when we study organic chemistry is it's all about the structure of molecules. So much of what we're going to see when we study organic chemistry is looking at the structure of these organic molecules and how they change as they undergo reactions. Okay? Kind of a good news, bad news thing. So, on the one hand, there's not any math in this course. There's very little math in this course. It's not really a quantitative science. On the other hand, there's this skill that we're going to have to learn, which is how to draw organic structures so that we can see how they change when we start performing reactions with them. And so very much so, that's where we're going to start this course, is how we represent these structures of organic molecules on the paper. Okay? We're going to start with one that's a little bit more familiar with you all, what are called Lewis structures. All right, but before we go there, we need to lay a little bit of groundwork with what's called valence electrons and the octet rule. Okay? So valence electrons. These are what are called sort of the outermost electrons in an atom. This has a little bit of a historical meaning more than it really being true about them being spatially furthest away. They do tend to be the largest electron orbitals, but really they're the highest energy electrons. And importantly, these are the electrons that participate in covalent bonding. All right, and let's just also sort of remind ourselves, by covalent bond, what do we mean? Covalent bond theory is insanely complicated, but we can kind of boil it down to one simple idea. If two atoms are covalently bound together, they are sharing a pair of electrons. So that word sharing, you really want to have tied in your mind to covalent bonds. So then which electrons are going to be shared if two atoms are bound together? They're valence electrons, right? That's a pair of electrons that are going to be shared. Non-metals in general, they really hold their electrons very tightly. So I think about a covalent bond as these two atoms are like engaged in this tug of war over this pair of electrons. Both of them are held together because they're both pulling that pair of electrons very strongly. All right? So we can tell how many valence electrons an element has just based on where it lives on the periodic table. All right? We can leave our staircase. Okay, so number of valence electrons. Everybody in this first column, and really the important one being hydrogen, because that's the one that's the feature of organic chemistry. We don't give a crap about the metals. Everybody in this first column has just one valence electron. We don't really care about the second column, but they have two. All right, when we're starting in on our non-metals, we're actually going to skip over the transition metals altogether. Again, we don't care about them, but also for our labeling here. Boron's column has 3 valence electrons. Importantly, carbon being the star of the show here, has 4 valence electrons. Nitrogen has 5, oxygen has 6, our halogens have 7, and then our noble gases have 8, with an important exception, helium. Helium's so teeny tiny small, it only actually needs 2 electrons to fill its valence shell. All right, it only has 2 valence electrons. We don't care about the noble gases either. All right. They don't form compounds with anything, never mind in organic chemistry, right? Cool. All right, so valence electrons. We can tell based on just the periodic table what element has how many valence electrons. Again, those are important because those are the ones that are participating in chemical bonding. Okay? So then why would an atom bother bonding with another atom? Why do they want to engage in this chemical bond? Well, because every atom wants to fill its quote-unquote octet. So it's going to share these electrons so that it can help to fill its octet, what we call the octet rule. Okay, so atoms will share electrons in a covalent bond to fill their octet. You'll also hear this called their valent, to fill their valence shell. We like to call it the octet rule because it reminds us that most elements want to have how many electrons to fill their octet? 8, right? That's the magic number for 99.9% of elements. We'll discuss some exceptions here, but we're going to say most elements want 8 electrons. So why is carbon forming a bond with hydrogen? So that it can fill its valence shell, getting to that 8 electrons. What's up?
Do noble gases already have 8?
Yeah, exactly. They already have a full valence shell. They have their octet rule satisfied. That's why they're not going to be sharing with anybody. Absolutely. They're not going to give up electrons. They're not going to accept electrons. They're like, get away from me. I am perfectly happy the way that I am. All right, there are some important exceptions here. The most important is the other central element in organic chemistry, hydrogen. Hydrogen is so teeny tiny small, it cannot possibly accept 8 electrons. All right? So in order to fill hydrogen's octet, again, a little bit of a misnomer, you only need 2 electrons. Another important, although we see it very, very rarely, but let's just put it on here for the sake of completion. Boron also is one of the smaller elements. Boron wants 6 electrons to fill its octet. All the other elements in the world want 8. All right? And you might be thinking, well, wait, in general chemistry, we learned about these expanded octet rules for sulfur and phosphorus. Drop it, don't worry about it. We're going to stick with these here. Simple rules here, okay? Cool. All right, so here's like kind of the basis behind chemical bonding, why these compounds are forming chemical bonds and what exactly they're sharing when they form these chemical bonds. Again, we're very focused on covalent structures, covalent molecules and the structures of those molecules. So what we're going to do is review the very first way that you learned how to represent molecular structures, what are called Lewis structures. Okay? And just to give you a little bit of a preview of where we're going here, by the end of next week, we're going to learn this organic chemistry shorthand for drawing structures called bond line structures. If you've ever seen just like the famous hexagon in organic chemistry, that represents an organic molecule. We could draw the Lewis structure here, but it's way faster to just draw what are called these bond line structures. So that's where we're kind of working towards, is to be able to represent these organic chemical structures, but using this shorthand here, Okay, but again, we're going to start with what we already know, which is the Lewis structure. And let's just do an example molecule. Actually, not an organic molecule, technically speaking, because there's no carbon in it, but nonetheless, very important for life. Okay, this is the Lewis structure for a water molecule here. All right, and importantly, we got these lines and these dots. All right, so first of all, we have these chemical symbols representing our hydrogen atoms and our oxygen atom. Right? These are just our chemical symbols. We also have these sticks here. These represent covalent bonds. So the sticks in our Lewis structure are showing us that these hydrogen atoms are bound to that central oxygen atom through a covalent bond. Importantly, each covalent bond contains how many electrons? 2. So covalent bond equals 2 electrons that are being shared. And then lastly, we have these little dots here. These dots are also very important in chemistry. These are also electron pairs, but they're not being shared. They're just sitting on that oxygen atom, what we call lone pairs. Also, they come in pairs, so each time you will see them paired up. 2 dots representing 2 electrons. And again, we can just make a note, these are non-bonding electrons. Okay? So in general chemistry, you learn this way of drawing these Lewis structures where you calculated the total number of valence electrons. You put the central atom in the middle, all the others around it, and you started doing some math with that number of valence electrons, okay? In organic chemistry, because we're talking about such a small subset of elements, we can kind of boil our rules down into a much more simpler subset of rules that we're going to follow here, all right? So when we're drawing our Lewis structures, we're going to keep this in mind. So electrons, elements like to have. All right, and I'll explain a little bit more about what I mean by like to have next class. For right now, we're going to take these as just hard, fast rules here. Okay? So again, we're going to focus on the elements that we actually care about in organic chemistry. We're going to make a little table here. This is going to be our little cheat sheet for drawing our Lewis structures. And for each one of these elements, we're going to keep track of the number of bonds that element likes to have and the number of lone pairs. Okay? And we're going to go across the periodic table. So again, the first one that we're interested in is that hydrogen atom. I guess we can put boron on here for completeness. Okay, carbon. 2 other very important elements that you see in organic chemistry are oxygen and nitrogen. These are absolutely everywhere. All right, and then the last one is the halogens. So for example, fluorine. All right, just to be clear, by the halogens, I mean anybody that lives in this column here. Fluorine, chlorine, bromine, and iodine. These don't play as big of a role in biochemistry, which are very much so kind of an organic chemistry-based chemistry, but they play a huge role in organic chemistry in the organic chemistry lab, right? Oh, this was an us, sorry. All right, so for each one of these elements, we're going to talk about how many bonds that element likes to have and how many lone pairs that element likes to have. And by using this simple set of rules here, we can draw our Lewis structures for these simple structures like water, but also more complicated structures that have a lot of carbons and a lot of hydrogens. All right? So hydrogen, being so teeny tiny small, can again only have 2 electrons in its octet, so it only wants 1 covalent bond, and it won't have any lone pairs. All right? That's enough. That 1 covalent bond is enough to fill that hydrogen's octet. Okay? Boron's a little bit of a weird one. Again, it's one of our exceptions. Boron likes to have 3 bonds and no lone pairs. All right, carbon, the star of the show here. Carbon, and the reason why carbon structures can get so complicated, is carbon likes to have 4 bonds associated with it. That's when carbon is its happiest, when it has 4 bonds and 0 lone pairs. I know I'm going to switch these. Sorry. In order on the periodic table, it actually goes carbon, nitrogen, oxygen. I got lost in my speech here. All right, but we're going to see sort of a trend if we put them in that order. So yeah, so switch these 2 compared to what I had originally. Sorry. All right, so nitrogen now. Nitrogen's already got quite a few valence electrons. It's already got 5. So because of that, it will form 3 bonds, but it will then have 1 lone pair associated with it, right? So whenever you see nitrogen at its most stable, it's got 3 bonds and then those 2 dots on it as well, 1 lone pair. Oxygen, just like in water here, likes to have how many bonds? 2. And how many lone pairs? 2. All right, and then the halogens, much like hydrogen, will only form 1 covalent bond, but distinct from hydrogen, they will also have 3 lone pairs associated with them. All right, so those simple rules that you learned in general chemistry for drawing these structures, they work great for very simple structures. They're more complicated than it needs to be in organic chemistry, and more importantly, they don't extend to the larger molecules that we want to be able to draw. If we keep in mind this simple set of rules here, we can draw pretty much any organic chemistry structure. All right, so for example, let's put this into practice here. I want you to draw me the structure of CH4. Okay, just to start using some chemistry sounding stuff. We don't know this yet, but this molecule is what's called methane. It's another one of those greenhouse gases that we're concerned about, particularly because it's emitted in high volumes in livestock, what do they call those? Fields, plants, farms, there we go. Livestock farms, so it's another molecule of concern. Okay. And then let's also do, how about CF2H2? Given the rules that we just laid out here, see if you can't draw these 2 structures. me show our rules here. Okay, in general, when you're drawing molecules in organic chemistry, you sort of want to start with the carbons. The carbons make up what's called the backbone of the molecule, the very middle of a molecule. And then you decorate with the hydrogens on the outside, because hydrogen only needs one bond, right? So the carbons kind of sit in the middle. The hydrogens are on the outside decorating. So I'm going to put my carbon in the middle. Again, carbon wants 1, 2, 3, 4 bonds and no lone pairs. Well, that's perfect because each hydrogen only wants one bond. So my methane Lewis structure here, I'm just going to decorate the outside with those hydrogens, right? And again, this just follows our simple rules of carbon needing 4 bonds and hydrogen only needing 1 bond. All right? If we jump over to the other one, again, carbon in the middle. Now I got some halogens in there, some fluorines. But how many bonds does each fluorine want? Also just 1. So just like hydrogen, they kind of decorate the outside. They can only have 1 bond associated with them. And then I'm done. No, what am I missing? The lone pairs, right? So the thing that's distinct about those halogens, they're quite electron dense. They have a bunch of lone pairs sitting on them as well. And I need to put a total of 3 lone pairs on each one of those fluorine atoms. 1, 2, 3. 1, 2, 3. What's up?
Was there a reason why the fluorines, for example, were on the top and to the right?
No, good question.
Across from one another?
The orientation on the page is irrelevant. What's important is who's bonded to who and where the lone pairs live. So what I mean by that is I absolutely could have just swapped these 2 around. I guess I would want to move this lone pair over. But that would have been perfectly sufficient as well. The orientation on the page is irrelevant. It's just who's bonded to who, where your lone pairs live. That's the important information that's conveyed in a Lewis structure. Okay, one more example I want to do is CH2O. Try to cram this in up here. Okay, so if we do this one, we put our carbon in the middle. We're going to start to decorate it with our hydrogens. All right, we got now this oxygen. I said oxygen likes to have 2 lone pairs. But what's the problem here? Carbon doesn't have its 4 bonds. Oxygen doesn't have its 4 bonds. Importantly, I can't just throw another hydrogen into this molecule because that's not what my formula says. My formula limits me to 2 hydrogens and 1 oxygen, right? So how the heck do I fix this? Does anybody remember? Double bond, absolutely, right? So we can also have not just 1 shared pair of electrons, but what's called a double bond. This is a covalent bond where there is a total of 4 shared electrons. Okay. And lastly, just for completeness here, a very similar sort of situation would happen if you tried to draw HCN. Here we have our carbon in the middle, hydrogen. We put our nitrogen down and we run into a similar situation. In order to rectify this, we would include what's called a triple bond. analogous to a double bond, we again have more shared electrons. This time we're sharing a total of how many do we think?
6.
Yeah, a total of 6. So 3 bonds, 3 covalent bonds, each one containing that pair of electrons. So here's a triple bond. Again, a covalent bond with 6 shared electrons. And there's no such thing as a quadruple bond, all right? So the highest order bond you got is a triple bond. And that's what we're going to see over and over again. Single bonds, double bonds, triple bonds. Those are what are going to be in our covalent molecules. Okay, cool. So that's all well and good, but these are still relatively simple compounds here, all right? So now let's do one that you wouldn't be able to do using your general chemistry rules. You're going to give me a structure for the molecule C3H8. Okay, so again, good strategy when you're drawing these organic molecules is to start with, again, what we call the carbon backbone. So I'm just going to link 1, 2, 3 carbons together. All right, so this carbon on the end here, it's already got 1 bond, so how many hydrogens am I going to put around it to make it happy? 3. And same with this one on the other end, right? That also needs 3. What about this one in the middle here?
2.
That would just need 2 hydrogens in order to complete its octet. Okay. So this would be the structure of what's called propane. If you have a propane grill when you're cooking with it, this is exactly the molecule that's powering that particular, particular grill. All right, and then lastly, let's throw another one in the mix here. What about C2H7N? Remember to go back to your rules for nitrogen. How many bonds, how many lone pairs does nitrogen like to have? And there are actually 2 perfectly acceptable structures that you could draw that have this same molecular formula here. All right, take a second, see if you can't think of the other one. Okay, so the one that I imagine everybody got first was they started carbon, nitrogen. They said, all right, this carbon on the end needs how many hydrogens? 3. 1, 2, 3. What about the carbon in the middle? Whoops. That one just needs 2. And then what about my nitrogen? That also just needs 2 additional bonds because nitrogen likes to have 3. And what do I need to finish off this structure? My lone pair. Okay. Now, importantly, if I pick this structure up and kind of flip it over like a pancake, so for example, instead I draw it N, C, C, these are the exact same. Okay, again, the orientation on the page doesn't matter. I could look at it like this, I could flip it like that, I could flip it upside down altogether. It's still the exact same molecule, right? So to be a distinct molecule, you have to have a different connectivity of these atoms. What's up?
Would it change the way that you wrote the molecule at the top? Like, you see at the top of the screen? See
This one here?
Yeah. No. Like, go down?
Oh, the formula here.
Yeah,
No.
formula.
Well, we will talk, so that's a good question. What I've been giving you these thus far are what are called molecular formulas. And all they tell you is the number of each atom. There is this, what we call the condensed formula, that does hint at the structure of the molecule. You would see that, and I don't want to confuse this here, but that would be something that would look more like CH3, CH2, and H2. So there is a way of sort of representing structure in that sort of straight line. We'll talk about that here in a second. Those are called condensed structural formulas. We'll get to that though. All right. Right now I'm just giving you the molecular formula. How many nitrogens, how many carbons, how many hydrogens?
I was just gonna say it just matches on like the carbon, how many hydrogens just wrap around it, and then the next one, right?
Yeah. Yeah, and then you go to the next carbon, and then you go to the next element. Yep. But we'll talk. It gets a little bit more complicated if it's not all in a straight line. We'll introduce these more formally. Okay. But again, to be a distinct molecule, you have to be connected. The atoms have to be connected differently. Did anybody get the other one here?
I did CNC.
Yes, exactly. With the nitrogen in the middle of that backbone. Nitrogen, unlike hydrogen or the halogen, the previous examples that we did, it can have more than one bond. So I could have said carbon, then nitrogen, then my other carbon. Fill that in with my hydrogens. I need to make sure my carbons again have their 4 bonds. What am I missing here? So I need a lone pair on that nitrogen. What else do I need? One more hydrogen. My nitrogen still has to have its 3 bonds. Cool. All right. So whereas these would be considered identical or the exact same, these two right here, this pair, let me use a different color, are indeed distinct molecules. They would have distinct boiling points and melting points and reactions. They are not the same molecule at all. They might behave pretty similar because they do look pretty similar, but they are not going to be the same molecule, all right? This is what we would call a pair of constitutional isomers. Constitutional isomers have the same molecular formula, but distinct connectivity of atoms. All right?
So if you put the N in front of the C on your molecular formula, would that change
No.
the structure?
No, the molecular formula is simply a total of how many you have. And really, the punchline that I'm getting at here is a molecular formula is an insufficient amount of information in organic chemistry because you could be talking about multiple different molecules. So unlike general chemistry, when you were writing your balanced chemical equations, and the only thing you were writing down were your were your molecular formulas, right? That's how you were describing reactions. We don't do that in organic chemistry. We draw out the structures because a molecular formula isn't enough information. I could be talking about multiple things. In this case, it's just 2. If I threw 5 carbons in there, all of a sudden we'd be talking about 25 different molecules or something like that, right? So again, just to hammer home the importance of structure here and why we're going to spend a whole week on how to draw these structures in organic chemistry, because that's what we're going to be looking at.
Are you primarily working with observing the physical properties?
Well, we're going to talk about both of each thing. So kind of how it works is we'll sort of lay down some foundation, and then we'll start talking about different functional groups, different classes of molecules. So then we'll start talking about alcohols and the properties of alcohols and the reactions of alcohols, what it means to be an alcohol, right? Organic chemistry is kind of divided into these clusters that we call functional groups, and we'll be talking about both physical properties but also chemical properties of these different functional groups. All right? We got a little bit of groundwork to lay before that. All right? Again, just kind of focused on structure. All right? Cool. That's all I got for you today. If you want to hang out and ask any questions, or you have any course questions or enrollment questions or whatever it might be, please come see me after class. This is a good place to get started. I just want to sort of remind y'all